Hello everyone, my name is Anya and today on Math and Science Concepts I will be talking about Newton's second law of motion, F equals ma. But before we begin, make sure to like, share, and subscribe and hit that notifications bell so that you never miss another one of my informative videos. So let's begin. Last time we talked about Newton's first law of motion. Today, we're going to talk about Newton's second law of motion. F is the force applied to an object. M stands for the mass of an object. And A denotes the acceleration of an object. The acceleration of an object is directly proportional to the net force acting on an object, is the direction of the net force, and is inversely proportional to the mass of the object. In summarized form, this is acceleration equals net force over mass. Continuing, the force acting on a moving object is the product of the mass and acceleration. Newton's second law states that the acceleration of a moving object depends upon its mass and the force acting on it. According to Newton's second law, an object at rest starts to move when a force acts on it. This force causes the object to accelerate in the same direction as the force. The acceleration depends upon two factors. One, the mass, and two, the force. Force is one of the fundamental properties of any physical system. The significance of Newton's second law is that it explains how to calculate the force. The fundamental characteristic of Newton's second law is the equation connecting force, mass, and acceleration. English physicist and mathematician Isaac Newton postulated that acceleration is directly proportional to the force and indirectly proportional to the mass. This hypothesis can be mathematically written as A equals F over m, where A is acceleration, F is force, and m is mass. From this equation, if the force on the object increases, the acceleration will also increase. On the other hand, if the mass of the object increases while keeping the force constant, the acceleration will decrease. Rearranging this equation, F equals ma. Therefore, the force is equal to the product of mass and acceleration. The above equation is the well-known form of Newton's second law. Suppose two objects have masses m1 and m2 such that m2 is greater than m1. If they are moving with the same acceleration, then forces F1 and F2 acting on them are given by F1 equals m1 times A and F2 equals m2 times A. Since m2 is greater than m1, we find that F2 is greater than F1. It means that a heavy object requires more force than a light object to accelerate by the same amount. Interesting, right? Now moving on to vector form. The force equation is written in scalar form. However, force and acceleration are vector quantities. Suppose the object is subjected to many forces, vectorially written as F1, F2, F3, etc. Then the net force is calculated by vectorially adding all the forces. F equals F1 plus F2 plus F3 and so on. Or equivalently, the net force is equal to sigma Fn. This force results in an acceleration A in the same direction as the force. Therefore, Newton's second law can be written in vector form as follows. F equals ma. Amazing, isn't it? Now talking about momentum, The Newton's second law can be written in terms of momentum, represented as P. Momentum is defined as the product of mass and velocity. P equals m times v. Since acceleration is the change of velocity over time, the force is given by F equals m times delta v over delta t, or F equals delta p over delta t, where delta p is the change in momentum and delta t is the change in time. Therefore, force is defined as a change in momentum over time. Moving on, we're going to do some examples on Newton's second law. The first example is a ball falls through the air until it hits the surface. The earth pulls the ball with a force given by the product of the ball's mass and acceleration due to gravity. This force is equal to the ball's weight. A heavier ball will experience more force. Makes sense, doesn't it? Our second example is a block of mass 3 kilograms is moving on a surface. A force of 25 newtons acts on it in the positive x direction, and a 15 newton force acts on it in the negative x direction. In which direction is this block moving? What is its acceleration? In this problem, we're given that m equals 3 kilograms, F1 equals 25 newtons, and F2 equals 15 newtons. Since F1 is greater than F2, the object moves in the positive x direction. The net force equals F1 minus F2, and this is 25 newtons minus 15 newtons, and this equals 10 newtons. Therefore, the acceleration is A equals F over m, which equals 10 newtons over 3 kilograms, because our found force is 10 newtons, and the mass that we were given was 3 kilograms. And this gives us 3.33, continuing forever with the 3's, meters per second squared. So we solved our first example. Our next example is a man of mass 80 kilograms on the top floor of a building steps into an elevator. What is the weight felt by the man as the elevator accelerates downward at a rate of 2 meters per second to the negative second power, where our gravitation constant is 9.8 meters per second squared? We're given mass equals 80 kilograms, acceleration is 1.5 meters per second squared, and this gravitational constant is 9.8 meters per second squared. According to Newton's second law, the force is given by F equals ma, our classic equation. Reaction force on the man by the elevator due to Earth's gravity is F1 equals m times g, which equals 80 kilograms times 9.8 meters per second, and this equals 784 newtons. Remember, newtons is kilogram meters per second squared. Force on the elevator by the man due to acceleration is F2 equals m times a, and this equals 80 kilograms times 2 meters per second, and this equals 160 newtons. Since the two forces are opposite each other, The net force is the difference between the two forces. Our net force, F, equals F1 minus F2, which equals 784 newtons minus 160 newtons, which equals 624 newtons. Therefore, the weight felt by the man is M equals F over G, which equals 624 newtons per 9.8 meters per second. Because remember, our force was 624 newtons, and our gravitational constant on Earth was 9.8 meters per second. And this equals 63.8 kilograms. Therefore, a person going down the elevator feels lighter. Amazing, right? And now we've solved our next example. So I'm glad that you made it through this video, and until next time, I'll see you with Newton's third law. Bye!